Hello everybody, we're looking at 2.4 limits and continuity today. So we're going to continue with our idea of limits, and as we've been talking about how most of the time, functions are continuous, but we tend to evaluate limits at those points of discontinuity, which is why we're getting indeterminate forms, maybe infinite answers. So we're going to investigate why. What does a function look like? What type of discontinuity does it have at those moments? So for a warm-up, draw a function for which the limit exists at x equals 2, but the function value does not equal the limit. So there's so many different examples that you could come up with here. I'm just going to show you one of them. Okay, I could have any kind of a curve with a hole as one example, and this is at x equals 2. I could have had that filled in circle or not, because right now I'm just saying that the limit exists at 2, but the function value does not equal the limit. Maybe the function value isn't even defined, but I decided to define it and then show that it is not the same as the limit. Right? Limit is always about the behavior of the graph. Usually when we talk about continuous functions, we say that they can be drawn without having to lift your pencil from the paper. Like, that's the simplest way to talk about it. This is because continuous functions don't have a break or a gap in them. So here's an example. What else does this mean about a limit? So if the function is continuous, then there always is a limit. And we further could say that the limit of f of x as x approaches c is always equal to f of c. So can a limit exist at a point in which the function is discontinuous? Sure, we saw this a lot in the last couple of sections. When we have a hole in the graph, and we're going to learn in a moment that that's a removable discontinuity, it exists. The behavior of the graph is the same around the limit, the point that we're evaluating, but the function value just doesn't exist right there, or it doesn't equal the general behavior. We also could have an asymptote. We could have infinite behavior. We would have to have a situation where the behavior on the left and the right of the asymptote are the same infinite behavior, but it happens. So this is simple but super important. In order to show that a function is continuous at a particular x value, 3 conditions must hold. We can't just say we sketched it without lifting our pencil. We have to show that f of c is defined, so the function is there. We have to say that the limit exists, and those two things are equal every time. The function's defined, the limit exists, and they are equal. So a removable discontinuity. This is the type that we have been investigating the most. These are the ones that we can algebraically manipulate and find an answer. So if the limit as x approaches c exists, but it's not equal to f of c. So key thing here. The limit exists. Okay. But it's not equal, we say that f has a removable discontinuity at x equals c. Okay, so our graph of some original function .
I'm all done.
At c shows a hole. We can always redefine holes by naming a function value and simply coloring or filling in that moment. Okay, I tried to make the graphs look as similar as possible. So we can make these functions continuous by redefining f of c as or equal to the limit as x approaches c of f of x. Okay, basically creating a piecewise function. So removable, aka whole. The next type, if the one-sided limits of a function exist, but they are not equal, the function is said to have a jump discontinuity. So there's a couple of different scenarios here. But this would be one of them, right? At this value of c, the left limit and the right limit are not the same. So further investigating this, if a function has jump discontinuity, it can either be left continuous, right continuous, or neither. So left continuous is notated limit as x approaches c from the left with that negative symbol of f of x equals f of c. So if the left circle is filled in, essentially, it's left continuous. Right continuous if the right-sided limit is equal to the function value. So graphically speaking, this is right continuous. This is left continuous. And this is neither. We have open circles. You may or may not have f of c defined someplace else. That wouldn't matter. And the third type is infinite discontinuity. So one or both of the one-sided limits are infinite.
Yeah, we're printing pictures.
So here's an example.
Wait, Mrs.
Here's an example.
Tarantino? Mrs. Tarantino. Is this science for us right now?
And here's another example.
Is this science?
Okay. Okay, I'm bringing in here some basic laws of continuity. These are things that we've talked about and seen in the past, but just as a quick refresher. First of all, if f of x and g of x are continuous at c, then the following functions are also continuous at c. So that's important. So we have two continuous functions. We can add them or subtract them, and the result would still be continuous. We can multiply by a constant k, essentially adding a coefficient, still continuous. We can multiply them, still continuous. Divide them, still continuous, as long as the denominator is not equal to 0 at c. Theorem 2 talks about continuity of polynomial and rational functions. So now we're just analyzing domain restrictions that we've seen in the past. So a polynomial is continuous on the real number line. The rational functions with two polynomials, numerator, denominator, is continuous on its domain. So obviously the restrictions occur when the denominator is 0, but everywhere else you're fine. We know that x to the rational exponent, so radical, is continuous on the domain for natural numbers. So if we have a square root, like a 1/2 power, for example, we know underneath cannot be negative, but so the domain is restricted at greater than or equal to 0, and therefore the range, it is continuous. Sine and cosine are continuous. Exponentials are continuous for base greater than 0, and logarithmics. So essentially what we're just saying here is think about all of the domain restrictions that we've discovered along the way. All of them hold true, and then if we're not dealing with a domain restriction, then we can assume continuity. Inverse functions. So if f is continuous on an interval I with range r, then f inverse exists, and if f inverse exists, then f inverse is continuous with domain R, right? So we switch those. Continuity of composite functions, if g is continuous at c, at x equals c, and f is continuous at g of c, then the composite, big F of x, which is the same as f of g, is continuous at c. So reread through those, make sure you're understanding them. We're taking all of the rules that we've already previously established in Algebra 2 and pre-calculus, and then we're naming these to be continuous functions given these restrictions. Okay. So now, here, I'm asking you to sketch a graph of f. At each point of discontinuity, determine the type of discontinuity and state whether it is left or right continuous. So we're looking at a piecewise function, right? You graph each piece and its domain separately, okay, and then we're going to evaluate discontinuities. So the first part of the function is the function x, which is just a line, slope of 1, and we're graphing this for values less than 1. So we need to really think about that end point, right? So at 1, the function would have an ordered pair of 1, 1, but it's an open circle because it doesn't have an equal to sign. And therefore, we now follow the rules on the left side of the graph for slope 1, y-intercept 0. Okay. We go to the next section. So the function's equal to 3, which is a constant, which looks like a horizontal line on the graph, and that is from 1 until 3, filled in circles, because we have the equal to symbols. And then, at 3 again, we begin this line of x. It's already filled in. It's the same ordered pair of 3, 3, so it continues like that. So I thought about these end points, 1, 1, 3, 3. This endpoint also was 3, 3. Having different endpoints indicates points of discontinuity or continuity for that matter. So we have one moment where if I went to the old definition of, graphing without lifting my pencil, I have one moment where I have to lift my pencil. That is when x equals 1. So at x equals 1, we have a jump discontinuity because the one-sided limits are different, and it is right continuous because the function value matches the right-sided limit. Okay, here's another one. Piecewise, we're graphing x squared for all values less than 2. Parabola, the end point that I have to think about, it stops at x equaling 2, and that ordered pair, taking 2 and inputting it into x squared, would give me 2, 4. So at 2, 4, I have an open circle. This is just the parent function for a parabola, so I know that I have a vertex at 0, 0. I have ordered pairs of 1, 1. I have negative 2, 4 for its symmetry. And my graph would resemble that. And then at 2, I'm equal to 6. So that's just a single ordered pair right there. And then between 2 and 6, I follow the line of 10 minus x. So my endpoints, if I take 2 and input it into 10 minus x, I would have 2, 8. Open circle there. If I take 6 and put it in there, I have 6, 4. Closed circle there. Okay. So now, again, I have a jump discontinuity at x equaling 2. And this one is neither, because my function value does not match the left or the right. Determine the points of discontinuity. State the type of discontinuity and whether the function is left or right continuous. So here I'm asking you to think about domain restrictions. We could get a sketch of this graph. We could have an understanding of that. We know that we're going to have domain restrictions for g at x equaling 1 and negative 1. Right? This is not a removable discontinuity. I cannot factor and cancel. I can't do any of those things. So if I graph it, those discontinuities are going to exist with asymptotes. Right? If I get the full graph, it resembles this. Okay, so in this case, I have infinite discontinuities at plus and minus 1. Different from the second one. The second one I can factor. I still have initial domain restriction of x can equal plus and minus 1, but I can remove one of them. So when I graph this, I'm really just getting the graph of 1 over x plus 1. Okay. So the negative 1 discontinuity remains as an asymptote. The positive 1 discontinuity is a hole. It's removable. You would see it in your table of values, but not on your graphing calculator. So at x equaling negative 1, we are infinite. At x equaling positive 1, we are removable. Okay. And this last one, cosecant of x squared, thinking about discontinuities. Well, thinking about what cosecant is equivalent to, so I'm going to write this as 1 over sine of x squared. So we have a fraction, right? Denominators cannot equal 0. So when is sine 0? Sine is 0 at 0. So therefore sine can equal 0. And at all pi's, or the square root of all pi's, I should say, because it's x squared. Right? So if I had in there x being pi squared, so then the square root of pi squared would be pi, and that would give me 0 in the denominator. So any repeated root n pi's are not allowed in terms of the domain restriction, and in a graph they come out as infinite discontinuities. So this is a well-known function, not overly used, but I'll go through it. So greatest integer function is a common step function. Brackets x is the function defined by bracket x equaling n, where n is the unique integer such that n is less than or equal to x, which is less than n plus 1. So for example, the example for me helps a lot more than that definition, but bracket 4.7 defaults back to 4. So any decimal, right, or fraction for that matter, between 0 and 1 equals 0. Any decimal between 1 and 2 equals 1. So I'm filling in the left side circle, but leaving the right side circle open, right? Because if I have 2 inside of this function, it equals 2, not 1. But if I have 1.999, that equals 1. So now anything from 2 up until not inclusive of 3 falls back to 2, and so forth. So this is called a step function. This has discontinuities at every single integer, and they are jump discontinuities that are right continuous. Okay, ignore this for now. Your assignment will be in the module. 3 types of discontinuity. Provide a graphical example of each. When is a function left or right continuous? So answer those questions to yourself. They're definitely in the notes. Take care, and I'll see you in class.